Hello and welcome to part 2 of the current feedback amplifier series. In part 1 of the series, I described how a current feedback amplifier's bandwidth depends primarily on the feedback resistance, resulting in a gain bandwidth independence. In this section, I will describe the second benefit of the current feedback architecture, namely its superior slew rate performance. In the next few slides, I will dive into the internal transistor level design of voltage and current feedback op-amps. An analysis of the internal design should give the audience a deeper understanding of why a CFB op-amp can achieve superior slew rate performance. Note that a detailed transistor level analysis is not important when designing an application circuit, but it does give the circuit designer useful insight into the device's operation. Limited slew rate is one of the shortcomings of a typical voltage feedback amplifier. A typical voltage feedback op-amp's internal circuit is shown here. The first stage is a high-gain transconductance block comprising the differential input pair Q1 and Q2 and the current mirror stage Q3 and Q4. The subsequent gain and output stages are lumped together as an integrator block consisting of an inverting amplifier and the compensation capacitor C. The amplifier here is configured in a unity gain configuration. Under normal conditions, the input differential pair is balanced and equal currents flow in each leg of the diff pair. During a slew rate condition, when a large fast transition occurs at the input Vin, the output is unable to track the input. The input diff pair becomes unbalanced and the entire tail current I will flow through transistor Q2 and into the compensation capacitor C, which subsequently starts to charge the output of the amplifier. The amplifier's slew rate is thus determined by the rate at which the capacitor C charges or discharges. For example, if I is equal to 100 microamps and C is equal to 10 picofarads, then the slew rate is the current I divided by the capacitance C, which in this case is 10 volts per microsecond. To increase the slew rate while keeping the capacitance C constant, the tail current in the input diff pair must be increased, but doing so increases the amplifier's overall power consumption. The limited slew rate will generally increase the settling time of the op-amp, which is a critical parameter in many applications. This figure shows the simplified internal circuit of a current feedback amplifier. Transistors Q1 through Q4 buffer the signal at the non-inverting input and drive the inverting input pin of the op-amp. Notice that the base junctions of Q3 and Q4 at the non-inverting input present a high input impedance, whereas the emitter junctions of Q1 and Q2 at the inverting input present a low output impedance. Using Kirchhoff's current law at the inverting node yields IN equal to I1 minus I2, where I1 and I2 are the push-pull transistor currents in Q1 and Q2 respectively. Transistors Q5 and Q7 and transistors Q6 and Q8 act as current mirrors. The current mirrors reflect I1 and I2 and recombine them at the high impedance node at capacitor C-comp. By mirror action, the current IC into C-comp is equal to IN. The resulting voltage across C-comp is buffered by transistors Q9 through Q12 to drive the output pin of the amplifier. When the amplifier loop is closed and an external signal imbalances the two inputs, the input buffer will begin sourcing or sinking the imbalance current IN to the external feedback and gain resistances. This imbalance is then conveyed by the current mirrors to capacitor C comp, causing V out to swing in the positive or negative direction until the original imbalance IN is neutralized via the negative feedback loop. Thus, IN is an error signal in the system. Now that you have a better understanding of how a current feedback amplifier works, I will demonstrate on the next slide why the current feedback op-amps have superior slew rates compared to their voltage feedback counterparts. Let's now examine what happens when an amplifier hits its slew limit in both architecture cases. When a voltage feedback op-amp is in slew, the amplifier's loop will open and the inputs will no longer track each other. In order to restore the amplifier to a closed loop, the inverting input will attempt to follow the signal at the non-inverting input, which subsequently means that the amplifier's output also has to track the non-inverting input. As described earlier, the current needed to charge the compensation capacitor and thus drive the amplifier's output is derived from the tail current source in the input differential pair. This is a fixed current and is usually in the range of microamps. The magnitude of the tail current in the input differential pair thus limits the amplifier's slew rate. A similar scenario plays itself out in the case of a current feedback op-amp, where the compensation capacitor needs to be sufficiently charged or discharged in order for the output to track the signal at the non-inverting input and thus restore the loop to a balanced closed loop state. The current IC needed to charge the compensation capacitor in this case is a mirrored replica of the error current IN at the amplifier's inverting terminal. This error current is derived from the amplifier's output stage, which in turn drives its low impedance inverting input. Amplifier output stages are generally designed to drive many milliamps of current and are thus much stronger drivers than the tail current source in a voltage feedback amplifier. Since IN in a CFB is much greater than IB in a VFB, a current feedback amplifier can achieve much higher slew rates. In theory, an ideal current feedback op-amp should have unlimited slew rate. However, the dynamic limitations of the input buffer and the current mirrors place an upper limit on the achievable slew rate. This slide shows a slew rate comparison between several TI products based on their internal architecture. Notice that the slew rate of a current feedback op-amp is almost an order of magnitude higher than a voltage feedback op-amp for similar levels of quiescent power. The products shown here are high voltage wideband amplifiers. The THS 3000 family of current feedback amplifiers represents some of the highest slew rate op-amps operable on 30 volt supplies available on the market today. Now that we know the basic internal structure of a current feedback op-amp, let us study the origin of the inverting input resistance, which we previously denoted by Ri. Remember that Ri plays a crucial role in the feedback transimpedance equation, and an ideal current feedback op-amp has an Ri of 0 ohms such that its loop gain depends only on the feedback resistance Rf and is independent of its gain configuration. The figure on the left shows the open loop input buffer stage between the non-inverting and inverting inputs of the op-amp. Resistors Re1 and Re2 are the emitter resistances of transistors Q1 and Q2 respectively, and represent the output impedance of the input buffer, which is also the input impedance of the op-amp's inverting input. The emitter resistance Re is a function of the emitter current as shown by this equation. When designing a low-power current feedback op-amp, the reduced tail currents in the input stage buffer will result in an increased emitter resistance. In low-power applications, the emitter resistance can exceed 100 ohms and will dominate the feedback transimpedance equation, which is not ideal. To mitigate the effects of high inverting input resistance in low-power current feedback amplifiers, Texas Instruments devised a new input stage by employing a closed-loop buffer. With a closed-loop buffer architecture, the emitter resistance is divided by the loop gain of the buffer, thus greatly reducing the input resistance from hundreds of ohms to less than 10 ohms. The table shown here compares the inverting input resistance of the wideband OPA 691 and the low-power OPA 683. The OPA 691 uses an open-loop buffer, while the OPA 683 was designed with a closed-loop input buffer. Notice that the closed-loop buffer helps in greatly reducing the inverting input resistance. One may ask at this point, why don't we always use a closed-loop input buffer like the OPA 683 if it helps in building a more ideal amplifier? The reason for this is that as the open-loop transimpedance bandwidth, or ZOL, of a current feedback op-amp increases, the bandwidth of the closed-loop buffer would also have to be increased proportionally in order to maintain Ri flat across frequency. This is not practical since a wideband closed-loop buffer consumes much higher power than its open-loop counterpart, and consequently the open-loop buffer is the practical alternative. In applications featuring low signal gains and large signal swings, configuring a current feedback amplifier in the inverting configuration may improve the linearity and bandwidth performance compared to the non-inverting configuration. I will use the THS-3091 as an example to explain this concept. Assume that the THS-3091 is configured in a non-inverting gain of 2 and is driven by an 8-volt peak-to-peak 100 MHz signal. The output of the amplifier will be a 16-volt peak-to-peak signal that requires a theoretical slew rate of 5025 volts per microsecond. In the non-inverting configuration, because of the virtual ground concept, both op-amp inputs will swing by 8 volts peak-to-peak, which requires the input buffer to have a slew rate of approximately 2500 volts per microsecond. In such a scenario, the buffer's nonlinearity will also contribute to the overall THS-3091's nonlinearity. When the amplifier is configured in an inverting configuration of -2 and an 8-volt peak-to-peak 100 MHz signal is applied at its inputs, the op-amp's output will still be required to satisfy a slew rate of 5025 volts per microsecond. However, in this case, both the inverting and non-inverting inputs will remain at ground. The input buffer in this case no longer needs to swing 8 volts peak to peak as in the non-inverting configuration, and therefore will no longer factor in the overall linearity performance of the amplifier. In this manner, the overall dynamic performance of a current feedback op-amp will improve when configured as an inverting amplifier. The inverting configuration may not always be feasible in a system design since it requires the previous stage to be able to drive a resistive load of Rg. The non-inverting configuration, on the other hand, always presents a high input impedance to the previous stage and thus doesn't suffer from the same limitation. The output noise model of a current feedback amplifier is shown here. The total output noise equation of a current feedback op-amp is exactly the same as that of a voltage feedback op-amp. However, there is a difference in the noise model of the amplifiers. In a current feedback amplifier, the non-inverting and inverting current noise are no longer equal. An example of the THS3217 is shown here. Notice that the inverting current noise is larger than the non-inverting current noise. The reason for this mismatch will be discussed on the next slide. The input stage of a current feedback amplifier is repeated here. The non-inverting input presents a high input impedance at the base inputs of Q3 and Q4. The mismatch between transistors Q3 and Q4 will determine the non-inverting bias current. Similarly, the bias current at the inverting input is determined by the mismatch between transistors Q1 and Q2. As discussed earlier in the presentation, the emitter inputs at the inverting terminal present a low input impedance. Due to the asymmetry in the input structure of a current feedback amplifier, the input bias currents at the non-inverting and inverting inputs are not well matched. Consequently, its bias offset current tends to be larger than that of a voltage feedback amplifier. The increased bias current at the inverting input also increases the current noise at the inverting input terminal. Voltage feedback and current feedback amplifiers have their strengths and weaknesses, and the appropriate amplifier architecture should be chosen based on the application needs. Voltage feedback amplifiers are more appropriate in systems that require good DC precision, rail-to-rail inputs and outputs, and low noise, low power, low to medium slew rates, and very low distortion in the sub 10 MHz region, or a combination of these requirements. Some of these applications include high-speed and precision ADC interfaces and transimpedance amplifiers. A current feedback amplifier is an appropriate choice in systems that require very high slew rates and large signal bandwidths, very low distortion at high frequencies, and in applications that require a nearly constant bandwidth across gain. Some of these applications include DAC output interfaces and line drivers such as those used for DSL and power line communications. This concludes part 2 of the Current Feedback Amplifier Precision Lab series. Thank you for your time, and please remember to take the quiz.